Today, a little lesson on some plumbing in greenhouses. I don't, I mean, we're going to go through a little bit of math, nothing crazy, but what I'm most interested in is you gaining a better understanding of some of the principles behind pipes and delivering water in a greenhouse. It sounds really simple, but you'd be surprised. So let's get into it. Definitely there's no leaks allowed. Yeah, that's definitely that's goofy, but whatever. Um, Units, again, we've talked about these before, but PSI is pounds per square inch. Once again, plumbing is an industry that relies a lot on the imperial system still. But greenhouses, probably more than most agricultural farms, because a lot of equipment comes from Europe, have a mixture of metric and imperial. But I'm going to stick to imperial for this lesson. Um, so there's some of the unit conversions between bar or kilopascals. And then in terms of volume, so down here at the bottom, we're looking at the volume. So up here is pressure, right? This is volume. Gallons per hour. A gallon is a paint can, right? So that's not a lot of water if it's 1 gallon per hour, but gives you an idea. So we're trying to understand how water moves through pipes, right? There's some fundamental things here that are worth understanding. So we're talking about flow, right? So how does water flow through a pipe over a long distance, and how is the pressure affected? Um, so when we're selecting pipes and pumps and all sorts of things, like last class we talked about pumps, this sort of dovetails well with that lesson because trying to size an irrigation system so that it functions properly requires a little bit of thought. And then there's just simple when in designing a facility. So a lot of greenhouses will build, say, 20 acres, and then a year later they're adding another 20 acres. Well, did they design the irrigation system so that it would expand simply into the future expansion that's planned? So making sure that you size your main water lines accordingly, right? Um, some other simple properties about water that sort of are fundamental is that water does not compress, right? Unlike gas, it's a liquid. Liquids do not compress. So like this syringe down here, when you press the plunger in, water is displaced immediately into the pipe. Now, of course, there's different pipe configurations. You have large gauge and thin gauge, right? So putting them side by side, for the same amount of displacement with the plunger, we've had very different outcomes at this end, right? This shot more quickly, covered a longer distance. This went a short distance. Same volume of fluid in both, right? So we're talking about velocity here. Velocity in the context of agriculture might have to do with, say, for example, pressure washers, which shoot a small amount of water at high velocity to knock things off things, versus a drain, which is a low velocity, high volume situation. Okay, so there's some fundamental shifts there. Another thing I want to talk about is pipe resistance. This is an experiment you've done many times. If you've had a scotch on the rocks or something, you stir your glass, the water does not spin indefinitely. It slows down, and that's because the liquid is interacting with the surface of the glass. And that happens in pipes. When you push water through a pipe, as the water interacts with the inside wall of the pipe, it encounters resistance. The longer the pipe, the higher the resistance. All right, and of course, in greenhouses, they get very long. That resistance can end up being significant. So that means that you need to maintain proper volume and pressure at the very end of the greenhouse, which means you have to design the pipes accordingly, and that's what we're going to go through today. I couldn't find a fancy picture on the internet, so I drew up this little graphic to help. But essentially over here we have like a water tank, and at the bottom there's a pipe with holes drilled in it. And if you just let the water shoot out, you'll notice that the water shoots higher closer to the tank and not as high further from the tank. And there's this sort of slope accordingly. And that's because we're dealing with resistance in the pipe along the distance traveled, which lowers the volume and velocity and pressure. So this is kind of what we're trying to make sure we can design a system properly for. That's also why we use pressure compensated emitters, right? The idea that we want all the water to come out evenly along the length of that pipe. So we use these pressure compensated emitters to make sure that happens, and we've discussed that before. Looking at a quick example, if you have a pipe with 60 psi pressure at the front of the pipe, right? And if it's shorter, you may have 58 psi at the end of the pipe, but if it's longer, it could drop significantly, say down to 47 psi. And if you remember from last class, certain types of irrigation equipment have minimum pressures to function properly. So we need to make sure that we have adequate pressure at the end of our pipes. So a lot of that is related to the length and the diameter, going back to my syringe example, right? So diameter plays a big role in that. There's lots of engineering tables. These are links you can use, and there's online calculators. I'm not going to get into that today. I'm just going to go through a couple of examples. So pick your pipe size carefully. Too small and you won't have enough flow. Large diameters, you could just put giant pipes everywhere, right? So 1 foot diameter. But the trouble is, pipes like that everywhere are going to be bulky. They're heavy. When they're full of water, your structure may not be able to support them. They block a lot of light if you're doing overhead irrigation lines. So we're trying to find the best balance that suits our needs without going overboard. Not to mention that the cost of pipe goes up as the diameter increases. And when you're ordering many thousands of feet of pipe, the price difference can mean thousands of dollars. So it's best to think this through. This is an engineering table giving you an example for a 1-inch pipe. So a 1-inch diameter pipe, and I've highlighted a column. So this is at 25 gallons per minute. That's a fair amount of flow. Well, that works out to 1,500 gallons of water an hour. That's like a quarter of a swimming pool. There's our velocity. We're not really interested in that. We're looking at our pressure drop is going to be 22.7 psi lost for every 100 feet of pipe. And our volume, which is one of the interesting things we look at, we measure as head. So I'm going to get into that in the next few slides, but the idea is, remember last week we talked about pumps and how they pump water up, and we measure that as the head height, total head pressure. And that tells us how well the pump can lift, how much pressure it's capable of. So when it comes to assessing pipes, we measure the resistance in terms of head pressure. So this pipe at the volume we're talking about is the equivalent of having a 52.4 foot head pressure on the pump for every 100 feet of pipe. That's pretty significant. That means the pump, it's the same, pump needs as much pressure to overcome pushing the water 52 feet straight up in the air as it does to move the water through that pipe for that distance. Let's look if we go up to a larger size diameter pipe. So a 1/2 inch bigger, so 1.5 inch pipe. Boom, all of a sudden for the same volumes, we're looking at only 5.7 feet of head pressure and only 2.5 psi pressure drop. That's a huge difference. So that's just a stark contrast of what I'm talking about here. I've put them side by side. So 1-inch pipe, right? This is 1 inch. You're looking at 52 feet of head pressure backwards against you and 22.7 psi drop in pressure. For the same volume of water, a 1/2 inch larger pipe has only 5.7 feet of head resistance and only 2.5 psi drop. So clearly for this kind of volume, 1.5 inches is the way to go. In fact, just looking at the chart, you can kind of see that around 600 gallons per hour is where things start to go south for 1-inch pipe. All right. So pipe resistance, right? Remember we talked about this, is just reviewing it again, right? So we measured pump performance based on head pressure. How high can it push it? And so we're talking about head pressure in terms of the pipe. So remember we talked about lift and we talked about head to get to the top of the greenhouse. Now we're adding additional head pressure for the length of the pipe that it has to travel. All right, so we're going to measure the head resistance over 100 feet of pipe, and we're going to measure the pressure drop over 100 feet of pipe to make sure that we have enough flow to run our sprinklers. All right, so in this case, just reviewing again, 5.7 feet of head pressure resistance over 100 feet of length. So that's for every 100 feet. So if I'm doing 1,000 feet, that's one of these for every 100 feet. That means it's 10 times this, so 57 feet of resistance over 1,000 feet. So if you're running pipes over 1,000 feet long, you probably need something bigger than 1.5 inches to keep that resistance down. So let's look at a scenario. Let's say we've got a pump and then a distribution line, and we've got 2 rows of sprinklers heading into a bay. Ooh, that's a terrible arrow. You'd think I'd get good at drawing with a mouse by now, but first of all, I'm left-handed and I mouse with my right. I know it makes no sense, but yeah, nothing about me makes much sense. Anyway, so we've got 2 lines. Oh, gee. And there's 40 sprinklers per line, right? So 40 of these things, and each one needs 18 gallons per hour at 40 psi to operate. Okay, those are our specs. Our gutter height is 10 feet, although I think later on I forgot that, so never mind. Relative to the rest of it, it's kind of peanuts. And if you add up the 400-foot pipe long and each 120-foot line length, we're looking at 640 feet total length of pipe. Okay, and if we look at each line has 40 sprinklers at 18 gallons per hour, that's 720 gallons per hour per line, which means a total of 1,440 gallons per hour. All right, let's look at our chart. We've got up here is the numbers. So we have 1,000, so 1,500 gallons per hour comes close to what we were talking about, right? So for 1.5 inch pipe, that's 5.7 feet of additional head pressure for every 100 feet. And we've got 640 feet. And 2.5 psi pressure drop for every 100 feet. So we do the math. Okay, there's a lot of numbers here, but it's really not as much as you think. So what we do is we take our total length pipe, 640 feet, right? We're going to divide it by 100 feet, and that means that that goes into 106.4 times. We know here that we have 5.7 feet for every 100 feet, so 6.4 times 5.7 means we have an additional 36.5 feet of head pressure resistance on our line. Okay, so that means, so let's say if you sized your pump for a total head of 20 feet, that's including, say, lifting from the pond and 10 feet to the gutter, we need to add another 36.5 feet for a total of 56.5 feet of head pressure for our pump to make sure it will suitably run the irrigation lines. So going back to those charts from last week, you would choose a pump that performs for the given volume and pressure at 56.5 feet of head pressure. Now let's look at the pressure. So again, it's 640 feet divided by 100 feet. It goes in 6.4 times, all right? We're looking at 2.5 psi of pressure drop for times 6.4, which means 16 psi pressure drop. So we need 44 psi. We need 40 psi, I believe, right? And we're starting with 60 psi, let's say, right? That means we've got 44 psi at the furthest stripper, which is enough to run the sprinkler. This is just another chart showing us the stark differences between a 3/4 inch pipe and a 1 inch pipe. My memory is finally not failing me, and I finally remembered this is my last slide, so I always get cut off right at the end, and then it's like, whoa, where'd he go? Anyways, but look at this, 3/4 inch pipe, 71.7 feet of head and 31 psi pressure drop for every 100 feet. So if nothing else, these charts will give you a pretty good idea of what size pipes you need for certain lengths to make it work properly. Some of you are going to ask, wouldn't you hire an irrigation company to do this? Absolutely, you would. And I'll tell you this, I'm kind of the kind of person where I'm not going to say I don't trust anyone, but I don't trust anyone. So I always do the math and check to make sure that I'm not paying a lot of money for something that's not going to work. Because if it doesn't work, they almost always have lots of excuses for why it doesn't work and how it's somehow your fault because you didn't inform them about something. So I'm just encouraging you to think these things through, especially if you're working at a smaller farm where you might end up with some smaller duties like putting in some dripper lines. Obviously, in a big commercial greenhouse, they're going to hire a big engineering company. I don't think you have to worry about this so much, but you never know. I've had students set up small trial areas where they have to do sort of one-off irrigation things, and you need to have an appreciation for roughly what size pipes to use so that the thing works and you don't get embarrassed.